Welcome everyone to the Marcus Wallenberg Prize Ceremony and Digital Symposium. I'm Dan Binkley. I've been a professor of forest ecology at Duke University, Colorado State University, and Northern Arizona University. I also had the great opportunity to spend a year at the Swedish University of Agricultural Sciences with a Wallenberg Professorship awarded through the Royal Swedish Academy of Agriculture and Forestry. It's my honor today to be the moderator for the Digital Symposium. We all have a variety of very important reasons for valuing forests, from picking berries and mushrooms to habitat for plants and animals, to the cycling of carbon, and of course the production of all the wood that leads to the vital wood products that we all depend upon. Swedes all know that mushrooms are more plentiful in some years than others, and they look forward to harvesting whatever nature provides each year. But when it comes to wood supply, we need a steadier supply from year to year, and so it's very important for us to understand what influences forest growth from year to year, from decade to decade, and especially from one location to another location. Today's symposium explores the groundbreaking ways that the laureates' work has contributed to joining the science and management of forest growth. We also go beyond simple growth of forests to consider the carbon implications and how our changing climates may affect our future forests. It's now my pleasure to hand over to Marcus Wallenberg. Marcus, please.
Most honored laureates, ladies and gentlemen, on behalf of the board of the Marcus Wallenberg Foundation, I am pleased to welcome you all to this year's Marcus Wallenberg Prize Symposium and, exceptionally, also the award ceremony. Unfortunately, we had to cancel the normal award ceremony and banquet due to the pandemic situation. We would like to express our gratitude for your continued interest in the prize, as its purpose is of the utmost value for enhancing the intended stimulating impact of the Wallenberg Prize on scientific research and technical development, supporting forestry and forest products industries. We are today honoring the 2020 prize winners. This is the 37th prize since it was instituted in 1980 by the shareholders of Stora Kopparbergs Bergslags AB. The prize selection process relies on high-quality nominations for the prize. The Foundation wants to express its gratitude to all those universities, academies, research organizations, and individuals all over the world which are nominating candidates for the prize. A key to the prestige of this prize is the selection process, for which the prize depends on a most distinguished prize selection committee. The committee relies on the engagement and support of a number of senior advisors and external experts. I want to express my gratitude to all involved. In April 2020, we were pleased to announce the result of the selection process, and I want to quote from our citation. The 2020 Marcus Wallenberg Prize is awarded to Professor Joseph Landsberg from Australia, Professor Richard Waring from the United States, and Professor Nicholas Coops from Canada, for the groundbreaking work in developing forest growth models based on tree ecophysiology and further development of these models to widespread geospatial forest analysis using remote sensing techniques. The work emerged in the 3PG model, which stands for Physiological Process Predicting Growth. It is today a tool used widely in both science and practice, predicting the growth of forests subjected to changing environmental conditions. In forest science, many models that have been used for simulating future forest growth have been based on trajectories of historical growth. This worked quite well if environmental conditions did not change so much. But now, when we see rapid changes in environmental factors fundamental for tree growth, like the atmosphere's increasing carbon dioxide, the warmer and sometimes drier climate, and greater risks of extreme weather events, we need to use new and better tools to predict forest growth. The 3PG model, in concert with its remote sensing expansions, has turned into a key tool in global and regional predictions of forest growth, forest health, and biodiversity development. Important to notice is that the work by the laureates has created a bridge between the conventional forest mensuration-based empirical models and process-based carbon balance models. This is timely and important due to the urgency to go all the way into more process-based modeling of forests, to be able to understand their current role in the Earth's carbon balance, as well as potential future roles dictated by the changing climate. It is of utmost importance that the political and regulatory discussion, for example in the EU, recognizes the role of the forests as both a natural provider of renewable raw materials and as a carbon sink. The work of the laureates is further a great contribution to open access science. From its launching, the 3PG model has been an open source tool provided free of charge for everyone. This has greatly supported its wide usage, and many users have made important contributions to its further developments over the years. Today, users range from the eucalyptus plantation owners to national authorities with a need to make predictions on the future developments of forests. In the symposium, two of the laureates, Professor Landsberg and Professor Coops, together with other speakers, will further explain and discuss the science behind and the applications of the awarded science. The Foundation is impressed by the research that we are honoring today, and not the least by the impact potential when also policymakers can access forest growth projections based on changing growth factors. Professor Landsberg, Professor Waring, and Professor Coops, please let me congratulate you for your outstanding scientific achievement. May I now hand over the diplomas to you, distinguished prize laureates. So, ladies and gentlemen, it's now my pleasant duty to present Professor Landsberg with the diploma. Congratulations, Professor Landsberg. And then I have Professor Waring. Congratulations, and it's so nice to be able to give you this award. Thank you. And also Professor Coops, congratulations, and all our best wishes from the Foundation. Thank you. Ladies and gentlemen, it's now my pleasant duty to ask Professor Waring to give the acceptance speech on behalf of the three laureates. Professor Waring, please.
Distinguished guests, ladies and gentlemen, we are indebted to the Marcus Wallenberg Foundation for this prestigious award, and most honored to have Chairman Wallenberg present the prize to us. During the 1990s, Joe Landsberg and I designed a model to track the storage and flow of carbon and water through forest. As a biophysical model, it was unique in one of its objectives: to predict what foresters actually measure: tree numbers, tree diameters, wood volume, and growth. To make the model practical, we simplified assumptions, data requirements, and eliminated the need for specialized software. Nicholas Coops added remote sensing and geographic modeling capacity to extend predictions across regions and continents. Initially, we wanted to create a reliable tool for forest planning and management. Ultimately, the impact of our model was much broader because it had the inherent ability to predict where forests are under stress as climatic conditions change. During prolonged drought, the calculated water balance in a forest approaches zero, and its trees are more susceptible to attack by insects and diseases. We found also that such places correspond to where megafires occur. Thinning a forest can increase its resilience to insect attack. The model specifies how much thinning is required because if conditions change too much, it will alter the composition of the forest. When we configured the model to compare the growth of one species with another under changing environments, it gained tremendous value to foresters and conservationists concerned about the future composition and growth of forest. It's these unforeseen benefits of the original model that led to our international recognition today. Joe and I are particularly indebted to Suni Linder, Stephen Running, and the late Paul Jarvis, who collaborated and inspired us throughout our long careers. We took advantage of many colleagues along the way and are grateful to them. Case in point, Dr. Peter Sands from the Commonwealth Scientific Industrial Research Organization in Tasmania completely rewrote the Excel software for the 3PG model before it went public. This software was key to the success of 3PG because we insisted, against the general policies of our respective institutions, to offer the model for free, along with the code and dozens of examples of simulations. That turned out to be a good marketing strategy, although we didn't anticipate it at the time. Jointly, the three of us greatly appreciate this international recognition for our modeling effort. This distinction signifies that scientists, through collaboration, can contribute both fundamental and practical tools for teachers, researchers, and decision makers. Thank you again for honoring us, our institutions, and our countries.
Thank you, Marcus, and thank you, Richard, for the introduction to the context that led to this year's Wallenberg Prize. There'll be more background and insights a bit later in the session as Joseph Landsberg gives a deeper perspective on the model. All models, of course, are simplifications of complex systems, and 3PG is no exception. Some simplifications of models happens when we don't have a clear process-based insight about some important factors that influence the growth of forests. Annika Norden is a professor at the Swedish University of Agricultural Sciences, and she's the director of Sweden's program called Future Forests and the deputy program director for a program called Trees and Crops for the Future. Future Forests is one of SLU's future platforms that combines disciplines in natural, social, and human sciences to research sustainable forestry. Trees and Crops for the Future connects basic and applied research in plant science to enable increased forest growth. Annika will consider some of the limits to our current understanding of factors that determine forest growth. Annika, please.
Thank you so much. It's so good to be here today. I've spent nearly 30 years in forest science, and never before forests have been so high on so many public agendas. Nearly every day here in Sweden we can read about the forest in the newspapers, and different stakeholders get to tell their story and their opinions and their feelings about the forest. So it's a good time to be a forest scientist. Forests are high also on political agendas. This summer, the European Commission presented its new forest strategy for 2030. This strategy is a clear shift from the previous EU forest strategies, with its clear focus on the grand challenges of today, climate change and biodiversity loss. The proposed solution to these challenges is to use forests to store carbon. For forests to store carbon, they need to take up carbon from the atmosphere. And that is, they need to grow. And it worries me that although we talk so much about forests these days in the public debate, we do not talk that much about forest growth. So today, in honor of our distinguished prize winners, I take the opportunity to talk a bit about forest growth. You can't talk about forest growth without mentioning national forest inventories, because these are used to keep track of how the forest grows. And in 2023, here in Sweden, we celebrate 100 years of forest inventories. And in Finland, the same celebration is going on this year. Technology on how forests are measured in these national forest inventories, that has of course changed over time, as you can see on these two pictures. But the basic sort of idea is the same. It's to measure how the forests grow, to make sure that we don't harvest too much of the forest. It is to make sure that we manage forests sustainably. And in the graph here, you see how the forest growth has changed over time in Sweden. And the graph starts in 1950s and is up until now. And we can see in the uppermost blue line that forest growth has increased over time. And the red line shows total drain. That is harvest, which is the black line, and natural mortality, which is the lowest yellow line. And as you can see, the difference between harvest and total drain has slightly increased over time, over the last 30 years or so. And this is, of course, due to increased natural mortality. That may be due to climate change. But forests' annual net carbon sinks is the difference between annual growth and annual drain. And this is what we talk a lot about when we talk about forests. Forest capacity to be a net carbon sink. And that is the difference between the growth and the drain. And we see the curves for growth and for drain for the 3 Nordic countries in this slide. It's Finland, Sweden, and Norway. And we start from the 1960s up until now. And for Finland and Sweden, we can see that growth is increasing over time, rather constantly, up to the last few years, I would say. While in Norway, growth has been leveling off since about the year 2000. And this coincides with the Norwegian forests. They have been allowed to age. And the portion of Norwegian forest in mature age classes is today much higher than this portion in Finland and Sweden. Also, if we look at the accumulated carbon stocks over time for the same 3 countries, we to the left see gigatons of carbon accumulated in living forest, that's the orange part of the graph, and in soils, the gray part of the graph, over this period from 1960 to 2017. And to the right, we see gigatons of carbon in the accumulated harvest. And this data tells us that at the same time as we have been harvesting forests in these Nordic countries, we have been building a net carbon sink in the forest. You could say that we have been eating the cake while at the same time increasing the size of it. And this all thanks to the increasing forest growth. So, going into the ecophysiology, I'm a trained ecophysiologist, and from my perspective, it is of key importance to understand the processes that direct forest growth and how these can be affected by climate change. And obviously there is no time to tell a complete story, so I will give you some fragments, and hopefully these fragments are interesting and perhaps also a bit new to some of you. But firstly, I've listed the abiotic factors that direct growth directly: solar radiation, water supply, carbon dioxide in the air, and availability of nitrogen supply and other nutrients from the soil. And it's really the relation between these factors that is the driver of growth. It determines growth in a specific place at a specific time. I will mainly talk about the northern boreal forest. Literally speaking, this forest is in my backyard, and I spent all my life in it. So, looking at this map, you can see which nutrient is limiting to plant growth over the globe. And the red color is nitrogen and the blue color is phosphorus, the two main nutrients that plants need to take up from the soil. And in the northern hemisphere and also in cold climate, high elevation ecosystems, it's nitrogen that limits growth, while in the tropical ecosystems and subtropical ecosystems, it's mainly phosphorus. So now I will tell you the story behind what's called progressive nitrogen limitation. And that is that as the carbon dioxide concentration in the atmosphere increase, this facilitates the photosynthesis, and then the nitrogen supply becomes even more limiting to plant growth. So you can say that in the northern hemisphere, we have more and more uptake of carbon dioxide that sort of makes the nitrogen more and more limited to support the forest growth. And that you can see in this curve, which is a modeled response to the increased carbon dioxide in the atmosphere. It's the increased photosynthesis efficiency that you see over time. Pre-industrial times it was lower than now, and it will level off now in the future. And this is what is driving this progressive nitrogen limitation. Another consequence is about the water. Plants take up water, and when it's dry weather, they close their stomata, their openings on the leaves, to hinder that water from going back to the atmosphere. Also, when they close their stomata, they will decrease, they will hamper the uptake of carbon dioxide. But as the carbon dioxide in the atmosphere is increasing, they need to have their stomata open for a shorter while to still take up the same amount of carbon dioxide. So they can, by that, save water. So increasing carbon dioxide at concentrations of the atmosphere will also mean that plants need less water, at least in some locations. The 3PG model, that provides an excellent modeling framework for projecting large-scale changes due to these small-scale processes that I've tried to describe here. And I would say that process-based models like the 3PG is really our key to understand the future of our biosphere. Recently, there have been some publications pointing out that the uptake of, the uptake of carbon dioxide in the northern hemisphere has been larger than what some of the models can project. And why this is happening is really one of these key problems. We don't really understand how the forest is growing at the moment in the northern hemisphere. To be able to understand that better, we do really need these process-based models. So, trying to wrap up, forest growth is the most efficient terrestrial process removing carbon dioxide from the atmosphere. And I see a tendency in the public discourse on forest that their growth is taken for granted. And as a forest scientist, I know it cannot. Forest management is key to sustained growth, as forest regeneration is a prerequisite for vital and growing forests. And we now see more and more scientific evidence in support for the great role of regenerating forests to keep them thriving. Also, as pointed out in this brief talk, there are still many unknowns, and we still need ecophysiological empirical research as well as modeling like the 3PG to be able to connect the small-scale processes to the large-scale happenings in the biosphere. And coming back to where I started, it worries me then that we talk so much about forests' carbon storage capacity without talking so much about forest growth. The European Commission is prompting for what they call closer to nature forestry that can be defined as a way to manage forest with continuous cover forestry. And this they promote as a one-size-fits-all solution all across Europe. And there's no scientific evidence base that such forest management would sustain today's level of forest growth. And in fact, particularly in the North European cold climate ecosystems, strongly limited by nitrogen, there is evidence that continuous cover forestry would in fact decrease growth. So my hope is that European forest scientists, that they would be allowed some time to really analyze the potential consequences of the presented European forest policy before it is put to practice. And this to ensure future-proof and science-based sustainable forest management in Europe. Thank you.
Thank you, Annika. Joseph Landsberg invested his career with Australia's CSIRO, the Commonwealth Scientific and Industrial Research Organization. As Australia's national science agency, CSIRO's mission is to solve Australia's greatest challenges through innovative science and technology. Dr. Landsberg was the chief of the Forest Research Division, and the 3PG model is a great example of fulfilling the agency's mission. This is also an impressive case of a government administrator continuing to be a remarkably productive scientist. Joseph, please.
Ladies and gentlemen, fledging is a word that applies to young birds. It describes the process of reaching a stage of development at which they can leave the nest. They can fly. It seems appropriate for a model which emerged from our brains, developed and then took off. But before I tell you about that, I want to add my thanks to those already expressed by Professor Waring to the Marcus Wallenberg Foundation for the award of this prize. For context, we need to appreciate the different points of view held by physiologists working in forest science and foresters. Physiologists are interested in the processes such as photosynthesis, respiration, and tree-water relations that underlie and determine tree growth. They try to explain differences in growth in terms of those processes, and a great deal of physiological research is at that level. It's not explicitly concerned with the growth of entire trees, even less with the growth of stands, although these are the outcomes of the physiological processes. Foresters, on the other hand, tend to be concerned with the management of forest stands for wood production. They need to know how much wood is in each stand and how fast the stands are growing. Forest inventories, measurement of tree populations and sizes, and evaluation of size distribution in stands have been carried out for more than 200 years in Europe. Sophisticated and complex statistical methods have been developed to analyze the data. These procedures result in empirical models based on observations and measurements that do not attempt to provide explanations in terms of biophysical processes for the trends and changes observed. These empirical models have provided foresters with the ability to project expected volume growth of stands, along with that of representative trees, from planting through to harvest, but only on the assumption that conditions affecting growth remain stable. Since empirical stand models provide no explanation for observed differences in forest growth, the reasons for those differences have to be inferred from supplementary information such as soil type and quality, site aspect, and rainfall amounts. Such inferences can only lead to general stand productivity estimates. Conventional stand growth models may be able, with sufficient empirical data, to account for management practices such as thinning or fertilization. However, they have difficulties accounting for defoliation caused by insects or diseases, or for responses associated with major shifts in climatic conditions. In 1997, Professor Waring and I, who had known each other for a long time, had the opportunity to work together in Australia, as he has outlined in his acceptance speech for this wonderful prize. We had both been committed for years to the idea of introducing more physiology into forest models, more of the mechanisms, the processes that drive and determine how fast forests grow. So we wanted to develop a process-based forest model. I had been in a series of senior administrative and management jobs and was back at the bench, or the desk in my case. We had more than 50 years of experience between us. We worked well and easily together and had about 6 months to see whether we could turn our rather vague ideas about process-based forest models into something satisfactory that worked. We were familiar with useful forest growth models that had been written by Steve Running, the Forest BGC model, and Ross McMurtry, biomass, among a number of others. We also recognized that process-based models serve as frameworks for physiological research, within which the different processes can be set in context and their importance and impact assessed. When we got started, things came together quite quickly. We worked through our ideas about how this model should look in the classic way, using whiteboards and pen and paper, discussed the problems as things took shape, and made decisions about how we might solve them. Several of those decisions were groundbreaking. I'll get to those shortly. The model we came up with, 3PG, Physiological Processes Predicting Growth, so 3 Ps in a G, was written as a deliberate attempt to bridge the gap between conventional, empirical, mensuration-based growth and yield models and process-based carbon balance models. That is, models written in terms of the basic processes that together control the amount and structural distribution of tree growth. We aimed to provide information useful to foresters, such as tree numbers, stem diameters, stem basal area per hectare, and tree heights. To ecophysiologists who might want to know about changes in biomass above and below ground over time, and to ecologists to explain why some species of trees might do better or worse in varying environments. 3PG was also written with the objective of producing a model that could be used in association with remotely sensed data to scale estimates of stand growth to regions. 3PG is a hybrid model because it combines elements of process-based carbon balance models with allometric constraints to ensure that biomass allocation reproduces typical observed patterns of biomass partitioning in the stand to produce output of immediate relevance to foresters. The time steps a month, and the data required to apply the model are basic and easily obtained. The biological core of 3PG consists of submodels for net primary biomass production, allocation of assimilates to various biomass pools, foliage, stems and branches, roots and stem population dynamics. It includes a submodel for plant available soil water. On this occasion, I don't have the time, nor would it be appropriate, to describe the detail of the submodels and the way they fit together and interact. That has been done in many papers as well as the original publication, and there have been many studies aimed at testing the various components. However, there are two submodels that probably warrant particular attention. The first isn't so much a submodel as an extremely useful empirical relationship which, though much disputed, has stood the test of time and lots of serious examination. This is the solution to the problem of respiration losses. Total canopy photosynthesis, or gross primary production, GPP, is calculated from a simple model of radiation interception by the forest canopy. More complex canopy photosynthesis models could be used, but a simple model does the job for monthly time steps. The effects of site and environmental factors on stand-level GPP are taken into account using a series of growth modifiers that account for the effects of temperature, soil water, and atmospheric vapor pressure deficit, soil fertility, and in more recent versions of the model, soil salinity and atmospheric CO2 concentrations. These modify the efficiency with which canopies convert absorbed radiant energy into carbohydrates. The actual biomass, net primary production, available for the forest growth is calculated as GPP minus the fraction lost by respiration. Numerous attempts have been made to model respiration in order to calculate that fraction, which obviously is likely to vary for all sorts of reasons such as stand type, age, and environmental conditions. But respiration models tend to be complex and demanding in terms of input data. In our case, Dick went off to the library and searched for the best published measurements or estimates of GPP and NPP in forest stands. He found 12 good data sets and with a little manipulation, plotted NPP against GPP to produce a statistically tight straight line with a slope of 0.47. So that's what we used in 3PG. That relationship has been attacked vigorously from the time it was published, but battered and bruised, it still stands as a good engineering approximation. The state of play is probably summarized by a recent review paper by Colalti and Prentice in 2020 that pointed out the shortcomings of the ratio, but ended up saying, quote, the average NPP-GPP ratio in over 200 studies representing different biomes, species, and forest stand ages was found to be 0.46. So we're not going to argue about it anymore. Sometime someone will no doubt write a respiration model based on appropriate physiological mechanisms at the same level of complexity, that is stands and monthly time steps, as the rest of 3PG, that produces a stable and accurate value for the NPP-GPP ratio. But to our knowledge, such a model does not yet exist. So our engineering approximation will continue to be used, although because the code for 3PG is open and freely available, anyone who wants to substitute their own relationship to calculate respiration and hence the NPP-GPP ratio is free to do so. The other important submodel in 3PG, which has been a major factor in its success, both as a practical tool and a teaching aid, is the carbon allocation procedure. This procedure allows leaf area index, a crucial variable because it determines how much radiant energy will be absorbed, to vary with growing conditions, but forces the allocation of carbon to stems and branches to follow patterns that lead to realistic structures. Carbon allocation is on a single tree basis. It depends on the fact that there are highly stable functional relationships between different parts of trees as they grow. These are called allometric relationships. They describe, for example, relationships between biomass pools and, conveniently, between biomass pools and stem diameters. Such relationships have been well studied and documented for a wide range of forests and forest species. In 3PG, the proportion of NPP allocated to roots in any growth interval is calculated first. It's strongly influenced by soil moisture and nutrition and varies from a minimum of about 25% to a maximum of about 67% of NPP. The procedure for allocating the remaining NPPs to stems and foliage ensures that the appropriate allometric ratios predicted for stem and foliage mass in terms of stem diameter at breast height are reproduced by the model. Stem diameter is a widely measured and easily checked variable. This is not the venue to discuss this procedure in detail. As I said earlier, that has been done in many papers, as well as the original publication. Also, a very thorough and detailed treatment of all this is available in the book I produced with Peter Sands, called Physiological Ecology of Forest Production, principles, processes, and models, if I may make a plug for that. 3PG is a conservation of mass model, so net primary production over any interval, which is the mass of carbon available for growth in that interval, must be fully accounted for. The equations for the rate of change of biomass pools are simple differential equations, each of which includes an allocation coefficient. The values of those coefficients must sum to unity. So that's the technical outline. So we come to fledging, an appropriate term for the process we went through in producing 3PG. During the development phase, as we settled on the relationships and equations we needed to make the model work, I programmed it as a large macro to run behind an Excel spreadsheet. I'm not a great programmer, so the result, although it worked well enough for initial tests and calibrations, and could be sent out to a few long-suffering friends and colleagues, was, as someone said, clunky. The model was a rather ugly nestling. But it was good enough for our colleague Nicholas Coops, who worked through the code and rapidly translated it into ArcInfo, so that by the time we published the paper describing the model, we, led by Nicholas, already had a paper estimating forest productivity across some parts of Australia and New Zealand using 3PG. Feathers were growing. The final step in the fledging process came when I sent the model to my very rigorous physicist friend and colleague, Dr. Peter Sands, who was working from Tasmania. Peter said he thought it was a good model, but would we mind if he reprogrammed it? We said, of course not. So he did. That was the point from which the bird flew. The model was fledged. The original paper has been cited more than 1,700 times as of early 2021. Peter produced a superb software package, a powerful, flexible, and adaptable Excel add-in. It generates graphics and almost any sort of data needed about forest growth as simulated by 3PG. Over several years, the package has been refined and provided with supporting notes, and the parameters in the model have been determined for a large number of species. Peter and I were adamant that the code should be freely available, which was always my position. Dick had no problem with this. Making software freely available carries the risk that people may alter the code, which anyone can do, and produce results from the model that we may not wish to be associated with. But as far as we are aware, that has seldom, if ever, happened, and the benefits of freely available supported software are enormous. It's available on the 3PG website along with Dick's full-class tutorial with examples we have assembled from around the world. We are certain and happy that making the code for 3PG freely available has been a major factor in its successful dissemination and use, both as a research and a management tool around the world. The model is an exercise in science and as such should be available to be tested and hopefully improved, which we believe is happening. We do not subscribe to the view that science is a commercial activity and therefore should be licensed and patented. It is a public, hopefully universally beneficial good. The Wallenberg Foundation provides a great service to forest science and the general community. The prize is an important part of that support. Thank you for your attention.
Thank you, Joseph. Nicholas Coops is a professor at the University of British Columbia and a holder of a Canada Research Chair in Remote Sensing. His experience includes a decade with CSIRO in Australia. His research is focused in large part on variations in forests across space and through time, and taking those insights and incorporating them into the 3PG model gave a quantum leap in the ability of the model to be translated from something that was very useful for scientists into something that could be incredibly powerful for management as well. Not only did he bring the opportunity to make things more spatially explicit, he also brought the knowledge and expertise of how to incorporate information from remotely sensed platforms into parameterizing the model for real landscapes. Nicholas, please.
Distinguished guests, ladies and gentlemen, I would like to echo my thanks, in addition to those from Richard Waring and Joe Landsberg, to the Marcus Wallenberg Foundation for this prestigious award. I would like to talk about how the 3PG model can be used from a plot scale, where it was originally developed, to be applied across stands to landscapes, and ultimately, globally, as a model of forest growth to help us understand the carbon allocation of forests today. Before I go into that, I would like to firstly recognise my co-award winners. Both Richard Waring and Joe Landsberg have been enormous mentors to me. And when I look up the definition mentor in the Oxford Dictionary, you could replace a trusted counsellor or guide with Richard Waring and Joe Landsberg. They have both been very generous over their careers with time and knowledge with me, and have ended up being strong collaborators for the research that I've undertaken since meeting them in the late 1990s. My many thanks to both of them. Joe has given a very detailed breakdown of the 3PG model and why it was so revolutionary at the time as a way of simplifying the concepts and underlying models that we knew at the time to go and build a comprehensive model that could be applied easily over space and time. Joe's acknowledged the important work of Peter Sands, who took the model and then put it into an easy-to-use Excel format. At the same time, we also started to apply the model and develop the code so that it could be run over large areas, working within a geographic information system, allowing us to go and apply the model across large areas, making landscape-level predictions, which are very useful for forest managers. More recently, we've seen a number of other model formulations of 3PG in programs such as R. There are many schematic diagrams that describe how 3PG work. Joe's touched on many of them. When you think about the input variables, though, that 3PG requires, there are a number which can be brought in as spatial variables rather than information from a plot. In 1997, we were just starting to see the development of spatial layers, spatially derived surfaces of attributes like climate, rainfall, temperature, solar radiation. And these spatial layers became critical to applying 3PG over a landscape. At the same time, we started to have very wide availability of terrain models, which provided information about slope and aspect. These are key drivers of the water in the landscape. And so these layers were also starting to be developed from satellite and topographic maps in the late 1990s. As a result, we started to see a shift from polygon-based inventories in forestry to more raster-based understandings. The idea that we would have raster layers or grids of climate that could come in at regular intervals. We could integrate that with information from satellites that were also growing at the time and link them together through long-term plots, such as permanent sample plots. This idea of a spatially explicit inventory was what we started to see coming up in the 1990s and 2000s. And 3PG was right in there as a model that allowed you to hang all these different spatial layers together. And of course, just at that time, we had a revolution in the availability of satellite imagery. Until then, we were fairly limited in the spatial images that we had from space. But in the late 1990s into the 2000s, we had an explosion in different remote sensing satellites that we could use. And I'll talk about how these can be integrated in 3PG throughout this talk. This immediate idea of linking in spatial layers was something that happened almost at the same time as we were developing the 3PG model. I remember working with Dick and Joe as they were preparing the Forest Ecology and Management manuscript, and thinking and discussing with Dick and Joe that there were many ways that remote sensing data could enter the model. And we started working immediately on applying the model in plantations in Australia for Pinus radiata. And here was one of the first simulations we ever did from that integration of 3PG with satellite imagery. We still have the incoming climate, but instead of allowing the leaf area to grow within the model, we use satellite estimates of leaf area index, which allowed us to produce patterns of forest growth at very fine spatial scale, much more than the polygons that we're originally used to that you can see in the top two figures. Now we're able to derive 3PG predictions of growth at a very fine spatial scale, 30 metres by 30 metres, giving us all the richness that the landscape has in terms of driving that forest growth. While we were doing this at the 30-metre scale, we were also looking at how to apply 3PG more regionally. Joe, based at CSIRO, and myself at the time started working with the Australian Greenhouse Office. And 3PG was used by the Greenhouse Office to go away and build productivity strata, but allowed them to go away and understand where productivity classes or gradients were occurring across the country at a very fine scale. This then led the development of strata where plots and additional analysis were put in to produce an Australian-wide carbon balance inventory. Likewise, in New Zealand, the 3PG model was quickly picked up by Landcare, again to stratify the productivity of the forests to allow new plots to be put in to represent that variation. 3PG was also being picked up within CSIRO, where it had initially been developed, and we started to see 3PG being applied at a forest management area. Here we can see the predictions that were undertaken in 2000 and 2001 for the Bago State Forest, which is near Tumbarumba in New South Wales. This was really the first time the 3PG model was being applied at a forest management unit to go and predict variables important for foresters like volume. This interest in 3PG was then growing. People were starting to realise that it could be applied at a plot scale, but also over large areas, and people were starting to integrate these GIS spatial layers. One of the first industrial companies to pick up 3PG was Aracruz Cellulose, based in Brazil. This work was pioneered by the work of Aro Amelia, who's now based at CSIRO, who went away and made predictions of short-term rotation growth of eucalypts within their estates in Brazil, as well as developing software tools to allow the plantation managers to predict what the future forest growth would be for the company. The real innovation here was not only applying it over large areas, but tuning 3PG to work in these very short rotations, in this case making predictions at 7 years for the eucalypt species. Applying 3PG then became more common to apply it over large areas. And this is where the work of Richard Waring, who then was back at Oregon State University, and myself about applying the 3PG model to larger areas of North America. We originally started in Oregon, which is where there was a lot of significant forest growth information and where we had a lot of other collaborators working at Oregon State University. We quickly found that 3PG was able to be calibrated for these conifer-based species in the United States, lodgepole pine, ponderosa pine, Douglas fir, and spruce, allowing us to go and make predictions for these conifer species across the region. We found that the 3PG model was again very accurate predicting key forestry attributes, in this case, the periodic annual increment of the tree growth. Excitingly, we also began to realise that we could model not only the growth, but the mechanisms of growth. As Joe described in his model breakdown, a key part of the 3PG was to build a soil-water balance model that linked to the dynamics of the canopy. Dick himself had done many years of work looking at soil-water balances in Oregon, so it allowed us to go away and compare the 3PG predictions of soil-water balance to measurements taken in the field. And here we can see a drier site versus a much wetter site as part of the Oregon transect, and 3PG is able to model the water and how that water is drawn down in the soil through the summer periods and then replenished again in winter. The rate at which that happens in the different soil types with the different vegetation types was able to be accurately reflected by the predictions of 3PG. This idea of using these modifiers then really interested Dick and myself, and we started applying the model more broadly throughout Western North America. And we started using not only the modifiers such as drought, but also the other modifiers that 3PG produced, for example, vapor pressure, temperature, and frost damage. At the time, climate envelope models for looking at species responses were very popular. 3PG uses those same ideas of climate variability and where a species fits within its niche, but by linking 3PG to radiation estimates and leaf area index, these modifiers are able to be scaled depending on the solar radiation absorbed at the time by the vegetation. This is an important distinction compared to traditional climate-based models which just use temperature and rainfall. As a result, we were able to make broad-scale predictions across all of Western North America for all of these different modifiers, for example, drought, temperature, vapor pressure, and frost. And we were able to track how different species within the Pacific Northwest responded to these different modifiers. So here you can see on the x-axis the seasons of the year, and on the y-axis the impact of the modifiers, where 1 indicates there's not much impact, 0 indicating there's very significant impact leading to shutdown and growth. Different species, for example, Sitka spruce, lodgepole pine, western hemlock, and western larch, respond differently to these modifiers. So as a result, we're able to go away and plot how these species are responding in their environment over long-term periods of time. In this case, for 30 years from 1976 to 2006. Where it's red, we can see that the species is comfortable within its given range. The climate in each individual year matches the long-term climate that species would expect. As we move into the greens, the yellows, the greens, and the blues, we start to see where the species becomes more stressed. In other words, the climate in some individual years is not well suited to the long-term climate of that species. That allows us to go away and work out where in the landscape the species is stressed. And Dick and I have done much work in the last decade, funded principally by NASA, looking at where we have these stress in species all across the Pacific Northwest. And by combining those for different species that we modelled, over 20, we're able then to go away and see where do we have more stress in our species, which is actually shown in the x-axis, and then using satellite data to go and look for examples of disturbances, for example, beetle infestation, fire, drought, and then comparing that to where 3PG sees that stress occur. What we find is where 3PG indicates the species is under stress correlates very well to where we see an above average increase in insect, disease, fire, and drought. All of those 4 variables then being observed by remote sensing. This work is still being actively done. In British Columbia, we started then to look at where should we be replanting seedlings following harvesting. As we know, we plant trees after harvesting as part of sustainable forest management, but the question now is becoming what is the appropriate species and seed source we should use to ensure that those seedlings grow well in a changing climate. In this thesis work by Amanda Mathis, she took this concept and she looked at where areas are stressed for a particular species, and then where the seedlings are being planted. And then finding a mismatch between the species that we're planting in areas that are likely to be more stressed, providing insights into where we should be changing the species mix across the landscape. Comparing 3PG to satellite-based imagery still today is an active area of research. Because satellites are able to observe these key variables that 3PG is able to predict, we can link those observations together. Here you can see on the left-hand side a prediction of the leaf area index over all of the Pacific Northwest of North America from 3PG. In the middle, we can see satellite observed leaf area index. So the 3PG estimate is what the landscape could produce given long-term climate and information. And on the right-hand side, it's what it actually is as observed from space. Now, as we know, there are a number of different input variables that go into 3PG. Climate, terrain, slope, and radiation are easy variables for us to go and obtain. Information on soil fertility and available soil water holding capacity are more challenging because our soil maps, even today, are not that spatially accurate. So in some work that Dick and I undertook in 2010 and 11 was to go away and try to link these two ideas together to use the leaf area estimates from space as the benchmark and then varying the predictions of leaf area from 3PG based on different soil inputs. With the logic being, if we had to increase or decrease the prediction from 3PG to match the satellite observation, we could do so by changing the soil attributes, which allowed us then to go away and make maps of the optimum soil attributes across the landscape. And as a result, we produced for the first time fine-scale estimates of soil water holding capacity and fertility across the entire Pacific Northwest. And these ended up comparing well to the traditional soil-based polygon maps that were freely available. A lot of the work that has been done has been linking the 3PG growth model to estimates of leaf area, because they've been readily available from satellite-based imagery. But today, in 2021, we have a wide variety of satellite imagery that we can plug into the model. And how we do that is still an active area of operational research today. Landsat information, which has been available in space since 1972, is driving our understanding of land cover, so we're able to bring in attributes like harvesting and management. MODIS provides leaf area index. We now have calibrated fine-scale long-term estimates of land surface temperature, which are resulting in evapotranspiration layers now being produced from satellite imagery. These can also be readily plugged into the 3PG model to see the water dynamics. We're starting to see more hyperspectral satellite-based imagery available, which is allowing us to directly predict attributes like canopy nitrogen, as well as light use efficiency, which can plug into the 3PG model to allow us to scale the growth depending on the productivity. And lastly, light detection and ranging, the use of lasers from aircraft and space, is giving us extraordinary information from a remote sensing point of view about biomass. So we're able then to go away and better calibrate the model in terms of those relationships between stem biomass, branch biomass, and foliage biomass, allowing LiDAR to be used to help build better allometric relationships. Like Joe, I want to highlight the fact that the success of 3PG model is due in no small part by the fact that it was freely available to use and modify when it was developed. Today, we're seeing a huge push for open source models and data to ensure reproducible science. The 3PG model in many ways was ahead of its time because that was 20 years ago when the decision was made to make the model publicly available. This resulted in very fast uptake and also ensured that people could modify the model as they wished for their own particular applications. If people wanted to improve the soil-water balance model, they could do so. If they wished to parameterize it for different species, they could do so. And then if they wished to parameterize it for mixed species, they could do that as well. As a result, the model flourished because it was freely available and available for people to modify it as they wish, without any contract or payment to make that happen. As a result, after 20 years, we now see it being the most commonly applied forest growth model used today. And whereas we started with that really important paper, the landmark paper of 3PG in 1997, 20 years later, we now have review papers about 3PG to help users continue to do it. And as recently as this year, we have full calibration parameters for a variety of species in Europe, as well as papers now reviewing the model and its application over that time. 3PG's success can be attributed to a large number of factors. Clearly, the openness and collaborative nature of Joe and Richard to see the model be promoted and used widely, the ability of the model to be plugged into geospatial information systems, allowing us to apply the landscape in management contexts, has attracted many people to its use. CSIRO continued to support its development, and of course many other organisations funded research projects to see the model flourish. So many collaborators, for all three of us, have been passionate about the model and to see it run. Too many to list, but they are of course from all over the globe, initially from Australia, United States, and now Canada, Europe, and globally, frequently use the model for a variety of forest management and forest research-based activities today. Again, many thanks for this prestigious award, and thank you very much.
Thank you, Nicholas. Professor José Luis Stape is one of the top experts in combining science and operational management in intensive plantation forests. He has been a professor with the University of São Paulo in Piracicaba and at North Carolina State University, where he directed the University Industry Cooperative Program in Forest Productivity. His role with Suzano Papel y Cellulose, the world's largest pulp company, has been to ensure that the scientific knowledge developed last year gets incorporated into operational practices this year. José Luis, please.
Thanks, Dan, for the introduction. Ladies and gentlemen, it's a pleasure to be here for the Marcus Wallenberg Prize Symposium. The presentation will focus on the importance of process modeling for fast-growing tree plantations. The goal is to show how foresters moved from simpler empirical model that predict wood growth to more elaborated hybrid model that describe the process that produce wood growth beside the other tree compartments, and the use of natural resources to do so, like water, light, and nutrient. More than that, I want to use this opportunity to show the importance of this modeling shift approach to speed up research and science for this kind of forest. Forest plantation is crucial for the wood supply globally. It's responsible for more than 80% of the wood supply worldwide. And its fast growth is impressive in some places with some genetic materials. And as we can assume, it's easy to see that the higher the growth rate, the more likely the profitability and the sustainability of these systems. The reason is that this area is not only more productive, but many research has shown that they are more efficient in using the natural resources. So, there are many examples across the globe, and we could pick up different countries to address this kind of forests, like Chile, Portugal, South Africa, Australia, China, and even the United States. But we decided to focus in Brazil because Brazil nowadays has more or close to 10 million hectares of eucalyptus fast-growing trees that will help us understand the history of modeling for this kind of force. For a forest perspective, wood grow is the main important thing for his business. But for a plant physiologist, understanding the process of photosynthesis or the process of root absorption for water and nutrient are the more important thing to describe growth. So, what is the way to do so? What is the way to approach wood growth in our reality? Well, it depends. In the very beginning of Brazilian forest development in the 40s, 50s, 60s, there was not a lot of science to be used for process-based model. So, for that reason and other that I will explain, empirical stem growth was the one chosen. Here we can see how fast was the improvement of forests in Brazil in the last half century. In the yellow shaded area, we can see the growth rate of forests was amazing, was almost fourfold increase. So, because of changing and improving the genomics and genetics, and changing and improving the silvicultures like site prep, fertilization, we were able to do that, and during this period, using empirical models that basically use the average of the last rotation to predict the next rotation was good enough. Evenly, or very often, the predicted growth was underestimated because the growth rate was so impressive. But as we can see at the end of in the last 20 years, there is a ceiling point, there is a plateau, there is a more likely limit of the site or of the genomics or the genetics that do not allow this kind of growth rates anymore. And that starts being a reason that predicting growth will start to be a more accurate science that requires more knowledge to be precise. More than that, as we know, protection starts to be in the last 20 or 30 years a big issue. Pest and disease spread globally. Different reasons, different hypotheses for that, but the fact is that there is no doubt that in Brazil, in the last 20 years, the number of pests and disease grows incredibly. And that's when you can easily see that, for instance, a defoliated tree that has wood in his stem will not grow for a long period until it refoliated. But the empirical model predicts a growth because it's based on the average of the last rotation. So, this error in prediction was because there is no link between the process of photosynthesis and the growth. The same we can speculate or we can do for rainfall. If there is no water in the system, the trees can die, can defoliate it, and they will not grow. And again, the empirical model could not handle that. Other appealing points. More and more the Brazilian society started demanding information about forest plantation. How much water are you guys using? How much nutrient are you uptaking from the soil? And from a lot of these questions, there was no answer because the empirical model was not related with any kind of natural resource use. And to get things worse, there is a lot of shortened rotations. I mean, increased the growth of the trees led to decrease the harvesting age. And when you have a short period of time, any disturbance by pest and disease or by water deficit or by any other kind of anomaly will cause a big effect on your final production. So that's when hybrid model start being seen as alternative to the typical empirical model. Being more process-based in general was associated or being more complex or impossible to be understood or impossible to be calibrated. And that's when people like Joe Landsberg and Richard Warren help a lot describing a model or developing a model like 3PG that lumped together complex concepts of physiology in a way that foresters like us could understand and use it on the benefits or better prediction and better understanding of forest growth. But this kind of modeling for sure would require adequate calibration, or mean adequate and robust design to collect data and test hypotheses about how this process works. That's how all begins. And that's how it starts shifting science. How come? So, to develop a system or to improve a model or to calibrate or parameterize a model based on process, we would start to need a different approach of science to measure not only diameter and height, but other process that is related with the tree growth, like allocation, for instance, root development, the effect of herbivory, and others. And the second point is these fast-growing trees are in different environments and they change very quickly. Every 5-7 years, you have a new plantation. And how we are going to deal with all these new calibrations we need for the next generations? Let's take the first question. And that I was lucky enough in 1999 to start my PhD with Dan Binkley and Mike Ryan at Colorado State University. And that's when we start thinking about forests, not just about tree growth, but also about the process that leads to this tree growth. Dan and Mike had already doing research in eucalyptus in Hawaii, and bringing this thinking to Brazil was a success. We were able in 2 years, manipulating water and nutrient, figure out how wood grow increase, and is completely different from our expectation. We expected that more water in the system will lead to more leaf area index and more growth. Quite the opposite. More water in the system leads to more efficient in using light and shifting allocation, and a very small portion to a little bit more leaves. And that's opened our eyes that this kind of study was essential to understand forest growth. At the same time, in other parts of Brazil, our colleagues was studying root development at one site with the same approach to be used to collect data to be used in forest modeling. But both studies was just located in one site. And given the good results, we were able to get together from 2001 to 2010 a group of 8 companies with many researchers and even university to test this water manipulation across Brazil landscape with different clones in 8 different sites. The results was amazing, and more people get engaged and want to learn how that works and how we could better model the growth of our forests. And then come the second project, TEX, where we were able to get together 36 sites with more than 24 companies, a lot of university students, to keeping addressing the effect of the landscape, the effect of water in the growth of different genotypes in different landscapes. All this research led us with a very good knowledge about eucalyptus growth in Brazil, the main effects and the way it responds to environment. And that was crucial to extrapolate the growth to other sites that was never tested. What was amazing for people from company that deal with exploring opportunities across Brazil to locate new mills, new forests, or even shifting the land base of the company. An example is this, where you can take different regions of Brazil, run different rainfall regimes, and with your calibrate process-based model for your specific clone, you can get different values for your yield. And that will tell you where your forest will die, where your forest will grow a little bit, or your forest will grow a lot. And that, as you can pick up, has a very good or a very important result for companies' investment. But let's get back now to the second question. If the company plant every year in different locations, new locations, different clones, different environments with different weeds, different pests, how we can handle modeling, process-based modeling that requires so much information or parameters. And for this, I will pick up the example of Suzano company, where the approach or the strategy was to install a network of 20 sites across the company, and each site not only water manipulation, but clonal manipulation, nutrition manipulation, space manipulation, weed control manipulation, and site prep manipulation. What's that for? To really provide insights about how forests respond to these different ecological features. It's important to highlight that this network used only 200 hectares across 2 years of installation. Only because during 2 years, the company has planted more than 160,000 hectares. So, with a very small amount of land, but well planned, we could address very important issues. As example, we were able to capture the G/E effect, and which clone is more sensitive to temperature or to water. We were able to capture, for the first time, the pests that occur across the company and their effect on the growth of the trees, herbivory. That was a kind of very difficult parameter to be used in modeling. Also, the weeds that varies along the sites were able to be captured, and all that information about root growth, herbivory, weeds, genomics, now is available to be used in process-based modeling in a way to improve it, but for the company perspective, because that's what matters for this specific case as Suzano. In parallel with all this development, the company or the companies has been investing a lot in orbital management. And it is important to show that the main use of orbital management is not only right away for operational purpose, but mainly for the long-term approach with process-based modeling. And for that, we do need a lot of information across the landscape. Knowing that, all these sites of the G2-M2P2 network and others was styled to be seen by space. So they are working not only as field trials, but also as orbital trials to gather better calibration for these satellites' image. So the point is that the future of process-based model is a kind of evolution. Each site, each company, each region will require its specific improvement. In this case, the way this example with Suzano company, herbivory, root growth, clonal specific behaviors will be important and is being improved on the 3PG model. Other companies has other challenges, like frost, other disease, and so forth. But one important message is that we do need to keep pragmatical approach, like we learned from 3PG. If not, there is a likelihood that this improvement will be not fully implemented in a pragmatical way. So with that, I finish my presentation, but I would like to highlight that all that was possible because the way Landsberg, Worry, and Coops think about 3PG to be a tool for development, a tool for learning. And if it was not that, it was not the open source of 3PG, probably I was not going to be here today talk about this amazing development of science in Brazil. Thank you.
Thank you, Jose Luis. Professor Julia Pongratz holds the chair of Physical Geography and Land Use Systems at the Ludwig Maximilian University in Munich. She is also the group leader at the Max Planck Institute for Meteorology in Hamburg. Her focus is on feedbacks between climate, vegetation, and societies, and dealing with these interactions using advanced Earth systems modeling. How do we go across scales from forests to regions to the globe? And how do we go across scales from the globe to regions to local forests? Julia, please.
Thank you very much for the invitation to the Marcus Wallenberg Symposium. So my name is Julia Pongratz and I'm from the Ludwig Maximilians University in Munich. And it's a great pleasure and really a big honor for me to speak here. But let me still take the time to really congratulate Joseph Landsberg, Richard Waring, and Nicholas Coops, because what they've done is really groundbreaking work. It's an amazing forest growth model. I think it's serving well beyond science even, and this is just amazing. So it's very well chosen laureates, and congratulations from my side as well. What I will show from our research is much coarser than the 3PG model. We don't go into species. We have much less well-constrained mortality assumptions. We are proud if we can distinguish a needle-leaf forest from a broadleaf one, and if it has coarse carbon pools that accumulate carbon. But still, our model, despite its coarseness, has some useful functions in that you can couple it to the atmosphere, and by that, apply it to global Earth system studies. And this is what I would like to show here today. So my story, in case you don't want to stay till the end, is the following. I'd like to show you that the humans have changed the extent of forest cover globally immensely. Then speak shortly about our future hopes for forests in that they should serve as big carbon sinks. And then show that the carbon aspect isn't really the only thing. There's biogeophysical aspects that are very important to also consider. But there's a big conundrum out there in literature. Even the IPCC special report on land said models are wrong because they disagree from observations. And I think I can show why that is, and that both models and observations are correct. And the takeaway message in the end is there's a large mitigation potential possible, though maybe not really plausible, but the adaptation potential may be huge and underestimated. And with all that, please note our perspective from the global Earth system modeling. On this map, you see the extent of forest cover worldwide in the absence of human interference. Now let's take out those areas that have been converted to agriculture. You see that about 1/3 of the forest cover is gone. If we overlay now the wild areas, you realize that still the majority of forest is remaining. About 60% of the forest that's still existing today is managed by humans or is degraded by human activity. And so you really see this human dominance on the ecosystem for forest worldwide. And these vast changes in forest area or forest management have severe consequences on climate. Why? Well, you can go basically everywhere because humans have influenced the vegetation cover everywhere. This is just outside of our department in Munich. Originally, this would have all been swamps and forests, but humans came in, cleared the forests, and now we have a big park, one of the largest inner city parks in the world, the English Garden. And you see that a forest, well, it's a tiny forest here in the middle, but let's take it as a forest. You see that the forest looks very different from the grassland around it. And this is exactly also what climate sees. So what's the difference? Well, first you, of course, realize that the forest seems to be much darker. The reflectivity or albedo is lower, and therefore it can typically absorb more solar light. Also, the forest tends to be rougher and also has a higher leaf area. And this combination makes that it usually transpire more, but also because it's rougher, it creates more turbulence. So the moisture, but also sensible heat can be transported away more easily into the atmosphere. Or conversely, could also mix down, for example, cooler air masses from above more easily than over the very smooth grassland. So these altered surface energy fluxes or altered hydrology, this is what we typically summarize as biogeophysical effects. And this contrasts to the aspects of carbon cycle. A forest takes up a lot of CO2, but then can also store it because of its woody biomass, which flat vegetation cannot do. Both in the biomass, but then also often in the soil, you have higher carbon contents than, for example, in an agricultural field, you often harvest. And this together with the nutrient cycles that I can't go into detail here, we call the biogeochemical effects. And these are the sole focus of politics at the moment. And I'll make a point out of that this is not a good thing. One reason for why politics focuses on carbon could also be that the biogeophysical effects are horribly complicated. Just look at this. From this albedo aspect here, you would really expect that the forest is warmer than the grassland because after all, it's absorbing more solar energy. But on the other hand, because it's rougher, transporting more heat away, it's cooler. And so which of these effects dominates depends very much on the season, on the tree species, on the region you are in. So this is very hard to get accurately into politics. Here's a proof that these effects matter, that albedo effects matter. This is a scene from the boreal winter, and you see the bright snow lying around apart from there where the boreal forest is. It's dark, and for most, the boreal forest is masking out the snow that is falling through the dark trees. And you really see these dark patches here. And here's a proof that roughness and the higher leaf area matter. This is the rabbit fence in Australia, and it's not that the rabbits influence cloud cover, but on the agricultural side, you've got flat vegetation that's not transpiring that much compared to the native vegetation on the other side that has a darker color, increased roughness, and higher convective mixing with cloud cover forming. So this much about the basics of biogeophysical effects. But we said that we really hope for the carbon cycle aspects to play out nicely in our favor in the future. That's what politically counts. It's the carbon. And this is what the Paris Agreement decided on in 2015, that we want to get down below, well below 2 degrees Celsius over pre-industrial levels, which would require that we massively reduce emissions, both from the fossil side and the land use side, but also will require carbon dioxide removal on negative emissions to some extent. Why? Well, first, currently, it doesn't seem like we're meeting the 2-degree target just with emission reduction. With the current policy measures in place, we're aiming still at 3 degrees. And second, even if we reach climate neutrality by the middle of the century, as would be required for a 1.5 degree target, afterwards, we may need carbon dioxide removal to compensate for too high earlier emissions, or we need to compensate for unavoidable emissions. And this all, again, requires negative emission technologies or carbon dioxide removal. The most prominent examples of carbon dioxide removal are natural climate solutions. Here is shown a compilation by Branson Griscom. Natural climate solutions sound better. And in fact, many of them are closer to nature and therefore less risky than many technological options could be that we just haven't investigated very well yet. Also, those natural climate solutions are at hand now, different from technological solutions that we first have to scale up in a distant future. So what can these natural climate solutions, these vegetation-based solutions deliver? Look at this compilation. You see the scale for the uptake of CO2 per year by 2013. And you see some big potentials. Here, for example, reforestation, up to 10 petagrams of CO2 could be taken up here per year. What I would like to point out here is that all those measures that have rather high potentials are based on forests, reforestation, avoided forest conversion, forest management. There's also measures on the peatland side, on the agricultural side, but forests feature very prominently. And you see that there's some pretty high estimates here. With 10 petagrams CO2 per year, we're still far below the emissions we're currently emitting with about 40. So there's clearly no way around emission reduction, but it could be part of a portfolio to help us smooth the path to climate neutrality. How do we get to these very high potentials? It's disputed how plausible they are. We ourselves have proposed a study that gets numbers like this, but it has strong assumptions. First, that the forest responds favorably to CO2 increases while not suffering overly much from extreme events. Looking outside the window here in Germany, it's not exactly what we see. The forests have suffered from 3 severe droughts in the last decade. And also what these high potentials would require is a high CO2 price to put value on forest and to create money that can go into intensification of agriculture. And only then could we provide the area at large scale for reforestation or other nature-based solutions like biomass plantations, for example, without interfering with food security. But it is possible. That's just a matter of the CO2 price. But again, carbon is not all that needs to be considered. So this was just a small excursion to the carbon realm. And now let's focus on the biogeophysical effects. We said they've been shown to matter too. Where? Well, first in models. A long time ago, already simulations like these came up. So here you see very hypothetical simulations with a global Earth system model that assumes that the entire forest cover of the world is cut down. Let's not hope this ever happens, but this is what it would look like in terms of surface temperature. So you see a bit of a warming in the tropical regions, but for most you see cooling effects. And you see them in the boreal regions, in the temperate regions. You see a cooling there, you see a tropical warming. So this is what models say about the effects of deforestation. And these results have led to warnings already 20 years ago that there may be an offset of the potential carbon sink from boreal forestation by decreases in surface albedo, and that this is something we should not consider as a nature-based solution. But then, here is the observational perspective. In the last few years, there have been several independent data sets coming up based on ground truth measurements, FluxNet data being scaled up, or top-down satellite imagery that also isolates the effect of deforestation on surface temperatures. You see that these 4 data sets here, they differ, but the general picture is the same. And so what observations say is deforestation leads to a tropical warming, but they also lead to a temperate warming, different from the models before, and to a boreal cooling, but really just in some boreal regions. So there's a problem here because the models and the observations don't agree. To reconcile models and observations, we need to take a closer look. And we need to distinguish local and non-local effects. What do I mean by that? Well, consider you're interested in one specific patch of forest. The local effects of deforestation would be if you deforest that patch of forest and check what the climate is altered like in that patch of forest. That's no longer a forest. The non-local effects would be if you clear everything else, but not your patch of forest, and then you measure how the climate in this patch of forest is altered, because these are the non-local effects of deforestation elsewhere. And these effects have very different relevances. The local effects, that's what affects local living conditions for humans, for animals, for plants, and therefore is a very strong, has a very strong relevance for adaptation. The non-local effects, that's what's relevant for the global mitigation potential. So to come back to our earlier depiction of biogeophysical effects, they start out to be local, but because moisture, heat, just like CO2 are transported off-site, they can affect the entire world and become non-local. They may also change atmospheric circulation and therefore have effects really across the globe. How can we assess them? How can we assess local versus non-local effects? Well, you could go out and cut forest. You measure the temperature where you've cut, and you measure the temperature in the forest next to it. The non-local effects will be kind of a background noise that cancels. So what you will be left with are the local effects. But this cutting down of forest does not work when the person with the chainsaw is an Earth system modeler. And when she forgets to take off the protective cover of the chainsaw. So we turn back to what we're good at. We turn to Earth system modeling. And I don't bore you with the details, but we've developed a setup that is able to isolate the local from the non-local effects in Earth system models. And I show you results here for deforestation again, but in your head, you can really just swap the sign to speak about the effects of reforestation on temperatures. So here, on the global scale, that's the nice thing about models, you can always do it globally and hypothetically. This is what happens when you deforest the world's forest. In fact, we've deforested just 3/4 of it. The local effects, they show you that there's some boreal cooling, but there's warming in the temperate regions and warming in the tropics. The non-local effects, they're interesting. They are much more widespread cooling. You see, even into the subtropics, you find a cooling effect from deforestation. It has many reasons that globally, the albedo indeed has been increased. Less solar light is overall globally absorbed. Also, there's less water vapor in the atmosphere. A variety of reasons play in there. But my point is, this is the answer to the conundrum that models and observations seem to disagree. Here, the observations again, just one data set now for comparison. Look at them and compare them to the local effects, and you'll realize that they really look pretty similar. At least in this pattern, you do see the boreal is cooling, but you do see that the temperate regions are warming, as are the tropics. And the reason there is that the observations only capture the local effects. It's due to the reason I've explained earlier, that when you measure two fields next to each other, the non-local effects are the background noise that cancels. So you cannot capture the non-local effects from observations. But the models, they capture everything. Like reality, there would be the local and the non-local effects. Only that in a specific setup, you can really isolate these two effects from each other in the models. And so let's go back again to these very old model simulations I've shown in the beginning. The models capture also the non-local effects, and this is because they create this big cooling even in the temperate regions. This is the reason why the models show a much more widespread cooling. So nothing's wrong, it's just a matter of perspective. But the matter of perspective is what is so important. Let's look again here at the maps of the local effects. And let's look at the scale of temperature. We spoke about warming and cooling, but let's look into how much warming and cooling there may be. And you realize the deforestation, and then again, let's swap the sign in our head, afforestation or reforestation can change temperatures by several degrees. And this is why I'm saying that there may be a huge potential to adapt to climate change by reforestation. Because locally, you may compensate for global warming that's out of your realm to mitigate, because you're just a small country in the big world. But to adapt to global warming, you can still make use of land use changes if you do it in a wise way. You still need to consider wisely in which region you are. And of course, what I'm showing here is not going into detail in terms of which tree species you could plant. There's other studies that have been doing that. There's models like the 3PG model that can really give you the results for the carbon cycle behind it for how the forest grows over time differently for different species. This is, of course, what needed to be done to really be policy relevant. But these are the foundations that show you the perspectives that you need to take to make sure that when we think of forests as a climate solution, we're not screwing up things. So I've shown you our massive impact on the Earth system, also in terms of forest cover changes or forest management. Our big hopes we place on the forest. And that's, yeah, there could be certainly a big potential to take up CO2 in forests. Even if we don't believe in the very high estimates, the forest will be an important part of a portfolio of CDR options. I'm convinced of that. But the biogeophysical effects are complex and we need to consider them. So the takeaway message, a large potential for mitigation is possible, maybe not very likely, but possible, but the adaptation potential by forest cover changes is huge. So I hope there will be opportunity for direct interaction with you in the future. Again, congratulations to the laureates, and thank you very much for the opportunity to speak here to you.
Thank you, Julia. Professor Geert-Jan Naboers is a professor of European forest resources at Wageningen University in the Netherlands. With his expertise in forest resource analyses and carbon sequestration, he's the coordinating lead author for the International Panel on Climate Change's report on agriculture and forests. We cannot know the future of forests with high precision, but our available science does empower us to try to avoid some mistakes we might otherwise make and to set up some valuable targets that we might be able to reach as we develop climate-smart forestry. Geert-Jan?
Okay, thank you very much. It's really a pleasure here to present in the seminar on behalf of the laureates. And given all the previous talks that you've heard now, I'm going to take you way up to the global carbon cycle and the role of global forests in the global carbon cycle. I'm Gert-Jan Nabius, I'm Professor European Forest Resources at Wageningen University. And apart from that, I've also been involved in many IPCC reports. Some of them you see on the slide, and currently we're just finalizing the 6th assessment report, which will come out early next year. Also on the role of forests and mitigation. Well, before we look forward, I'm going to take you a little step back into a bit of history. And here you see a paper that we published in 1992 with my senior Frits Moore. And it was on the role of forests in mitigating climate change and a modeling analysis of forest types around the world. And it was already in that time that one of the Dutch coal-fired power plants, they wanted to compensate their emissions by planting forests around the world. And that has, we analyzed that, what they could do, and that has been put into practice. But what I thought then, I was very junior, and I thought, well, carbon and forest, that's going to go away. There will be different subjects in the future. But I was very wrong about that. And still, I stayed in this field very much, but I was very wrong thinking that. So I'm going to take you very quickly through the role of global forests in the carbon budget, something about uncertainty and monitoring, which is part of the land use and assessing what the land use is doing. And then a little bit on to what degree can we actually change that balance? And can we, with forests and forest management, can we change the balance of carbon to mitigate climate change? And then some very quick conclusions. And this graph you will have seen many times, I guess. This is the buildup of carbon dioxide concentration in the atmosphere as measured by David Keeling starting in '58. Now reaching something like 410 parts per million in the atmosphere. And it's not the curve so much which I want to point at, but there were a couple of surprises for them, what came out of it. One of the surprises was the seasonal fluctuations, which you see in the graph. So apparently the northern hemisphere and the northern forests thus really had an impact on the carbon dioxide in the atmosphere. And the second is that they knew the emissions from fossil fuels pretty much. They knew by this curve how much was building up in the atmosphere. They knew reasonably well how much was building up in the oceans. But in that balance, there was a huge gap. There was a big missing sink, as it got that name. And this is when this first notion came up that forest and land use play an enormous role in the carbon cycle. And this missing sink has really driven a lot of research after that. So this is now a more recent graph of a budget, a CO2 budget. On the left you see the emissions from fossil fuels to roughly 34 gigatons of carbon dioxide, but also land use change, mostly deforestation in the tropics, emitting additional carbon dioxide into the atmosphere. So that carbon has to go somewhere. The carbon atoms don't go away. So what we think now, what we see is that, almost half of that builds up in the atmosphere. A quarter is taken up by the oceans, and then there is this 30% that is taken up by land, and mostly forests, what we believe. And this CO2 uptake, what is going to the land, has led to really a huge debate on where is it going? Is it going in the north? Is it going into the primary tropical forest? Is it the land management that is actually doing this? And to what degree has actually this uptake also been stimulated by the CO2 fertilization in the atmosphere? That has really led to a lot of debate. And here you see a graph where on the plus, this is the emissions from fossil fuels and land use change, and in the minuses is where the carbon is going. And the green part is the carbon dioxide that is sequestered on the land. And what is characteristic here is that there's big annual fluctuations on how much carbon is actually taken up on the land, determined by the weather circumstances in those years. Now a little bit step towards uncertainty. and monitoring, can we actually say where this carbon is going? And now I'm using this, well, you may remember a paper by Tom Crowther a couple of years ago, 3 trillion trees on the world. So I tend to say there are 3 trillion trees and we're still counting. And the picture, you see a colleague of mine in the National Forest Inventory in the Netherlands. And well, one of the main assessment methodology has been national forest inventories, converting those stem wood volumes into carbon. And when you do repeated inventories, you can assess a carbon balance. Still with its uncertainties, even though national inventories are very precise, but then all the additional steps lead to uncertainties. And these assessment methods have really developed very much over time. There's a variety of methods. In the top left, you see the national forest inventories that I just mentioned. In the bottom, you see eddy flux towers. There are a very limited number of locations in the world where a flux tower is directly measuring the CO2 uptake above a canopy. On the top right is more one of the laureates, his field, Nick Coops, the role of remote sensing and new, certainly a lot of developments, new developments there based on remote sensing, assessing also the dynamics in the forest, with advantages and disadvantages on all these methodologies. And on the bottom right, you see where a lot of these, the knowledge, also, for example, the 3PG model is there from the laureates. A lot of these modeling analysis on the role of forest and forest management have also developed very fast over time. But all these methods have their pros and cons. For example, remote sensing is very good in assessing a cover loss of the canopy, but the cover gain is much more difficult. And all these methodologies thus give a very large variety of how the global forest sector is functioning at the moment. And this graph shows there in the plus, it's a net emission. So the blue line there on the top left is from the integrated assessment models, who are very much based on these modeling approaches, but also on the cover losses from remote sensing. They assess the role of global forest even functioning as a net source, even when you take into account all the regrowth and management aspects. But for example, on the gray line, fluctuating around the zero, this is how the national greenhouse gas inventories assess the role of global forests. And you see an enormous gap there of 5 gigaton of carbon dioxide uncertainty because of different methodologies, partly understood why these methods give differences, but partly also not understood why these differences are there. And this uncertainty really hampers if we want to get activities going in order to strengthen the role of forests in mitigation. The uncertainty really hampers to get activities going, because you will not be rewarded if you have a huge uncertainty in the current understanding of forests. Given this uncertainty, so to what degree can we actually change the balance? And I'm just going to use a few global studies. There have been many studies about this. Let's say on the role of forests, the Paris Agreement does mention the role of forests, but in a very vague way. It's certainly not determined to what degree forests can be used to meet the commitments. But here you see 4 future scenarios of how emissions need to be turned into a net zero balance around 2050 or 2060. And the gray is the fossil fuel emissions, which really need to be taken down. And the left graph is where you manage to do that very rapidly, and then you don't need a lot of things on the land. But on the right, you see what is called an overshoot scenario, where we do not manage to really reduce the fossil fuel emissions. And that means if you cannot reduce your fossil fuel emissions, you need to take more and more measures on the land. And that's the yellow negative numbers that you see on the graphs there. So less you can achieve with fossil fuels, the more we will rely on the land. And that is a big challenge. And here's another a paper where I was also co-author with Stephanie Rowe on the contribution of this land sector in achieving those targets. And in all the global studies, it comes out that the role of land is very important in achieving these targets. And that's the green wedge that you see there, and on the role of additional mitigation in the land use sector. Characteristic for these measures is always that it's a huge variety of measures that you can take, very much dependent on the local circumstances, very much also dependent on other needs of forest, other needs for fuel and food production, and certainly also other needs on protecting biodiversity. And it's that whole set of functions that the land sector fulfills. It's within that set that the mitigation needs to be established. Okay, now we're going one step from the global, we go to a European, a bit more concrete measure, and this is a European tree species map that we, in our Wageningen group, we have a lot of European scale resource analysis with the EFICEN model, and this is from the EFICEN model. Characteristic for Europe is, of course, that we have a lot of managed, young and regrowing forests. This has been the notion since the 70s, 80s, 90s very much, and the build-up of carbon all the time. But this notion is also changing, and this is a paper we did with Mark Hanewinkel on climate change impacts and what the economic impacts may be on the European forest sector. And in red you see where spruce can grow now in its climate envelope, as we call it, and I will scroll through the timer, and the year now says current, and then it says 2010, 2040, 2040, 2070, and 2070, 2100. And you see that under a rather strong climate scenario, there's absolutely no chance for spruce in Central Europe to survive, where spruce is now very important, and even southern Scandinavia, it cannot survive. And these are dramatic changes, and we thought with our modeling, well, this is 2050, still far away, and it's a model with all its uncertainties, but however, the actuality is that spruce is already dying in Central Europe. And this is a picture from the Harz, where all the brown is, of course, dead spruce. And because of the drought in just 2-3 years, 2018 till 2020, bark beetle has developed massively and leads to massive mortality. More than 200 million cubic meters already dead and rapidly expanding still. So climate change is not something from 2070, but it's right here already now. And this poses large challenges for the sector to adapt to these circumstances. It's not always as dramatic as in the picture, but it's also the more subtle environmental changes that also change the forest resources. And this is a graph where you can see on the right, for example, in the gray shaded area, this is how it was expected that oak stands will develop growing stock over time according to yield tables, but the dots are the more recent measurements, and you can see that the dots are way over the outside the yield tables. The environmental circumstances have changed so much that trees are growing much, much faster than what was always measured in the past. These are the subtle changes which may also become more drastic in the future. A little bit on the role of forests. Well, very quickly, European forest, as I said, is a regrowing resource. We analyze this, and we call this, if you take a climate-smart forestry approach, the current role of European forests of compensating 10% of the fossil fuel emissions, you could almost double that contribution, close to 20%, if you invest in your forest management, in your resources, use wood sustainably. A little bit of forest reserves are there as well, but this variety of forest management options, that is what we analyze for Europe. And in that variety, that's characteristic for climate-smart forestry. You really look at the local circumstances, what is best to do. And just one example that I want to show again how fast things are changing at the moment. This is a picture from Czech Republic where a clear cut was done because of the spruce decline. And in the front you see that people have planted beech. This is a climate smart forestry run that we made with the EFISAM model, and in the dashed line is how the country is reporting to the UN now its sink. So the negative is a sink of roughly 10 million tons of CO2 in the 1990s. And in the climate smart forestry scenario, in our projection, you can see that it becomes very difficult to maintain that sink because of the bark beetle problems and the loss of forest and your necessity to change the forest resource. You can see that in one of the lines we are even above the zero, so we project a small source for some time. It's very difficult under these circumstances to maintain a sink. That is what we modeled then, but a few weeks ago I updated the graph. And this is what the actual measurements now look like. If you look at the dashed line, this is how Czech Republic has projected or has reported to the UN its current forest sink. And the sink, as you can see, it has changed massively into a source. And this is the first time that a European country, maybe since the last 50 or 60 years, is massively acting as a source of carbon dioxide. Now, a little bit more, and I'm almost there. We came from global forests, went to European forests, and now down to even something like a small forestry country like the Netherlands. And this is one of our PhDs in a walnut trial in the Netherlands. So we're actually applying this climate smart forestry in various ways. And this is what we are doing in our group. We have a group of, luckily, some 15 very young and enthusiastic people. We implement, one of the things is to implement this climate smart forestry idea in Dutch pilots, and basically it comes down to more forest, better forest, and a little bit more with wood. And that's the large integrated program that we are running. We are, for example, revitalizing poor Scots pine stands on poor sandy soils that you see on the top left. Working more with mixed species, selected provenances, adapted species. That's what we're doing. On the right bottom you see a picture of a linden regeneration area. Those are the ones we are implementing together with the sector. We also analyze how the current forest is acting. And since the 1980s we have 60 small reserves in the Netherlands. And so we analyzed, on the left you see a reserve established in the 80s. It was an existing Douglas fir stand, but then it was made into a strict reserve, and it became a hugely growing resource, with more than 1,000 cubic meters per hectare in the Netherlands, which is very, for us also very new. And you see then on the lines the yellow and blue, if you would continue your regular management. The thin gray line is if you use your wood and substitute other like steel and aluminium, there's a substitution effect, so the gray line is developing over time as well. But the reserve so far has grown really very fast. So in terms of carbon, the reserve keeps on building carbon stock, at least for the time being, these 45 years. It was also analyzed on biodiversity, but on biodiversity the reserve differed almost nothing, or well, maybe some groups of ants. It differed a little bit compared to regular management. On biodiversity, the reserves actually didn't show any significant difference with a regular management. And this is what you can later look at. These are all the pilots we are executing. And there is an online toolbox on climate smart forestry. There's also a European network developing on climate smart forestry with many groups across Europe, and this is what we are pulling as well. Now, given the time, what I want to say that since this 1992 paper, the global forest sector has changed enormously. has certainly made big contributions, but things are really developing and changing very rapidly, as I showed with, for example, with the spruce problems. A lot of talking about the role of forests and mitigation, but in practice, because of the policies, not much has happened really in the land use sector. And that is characteristic for the land use sector. It's very difficult to get things going. Given the millions of owners, landowners that you're dealing with, the various functions that you're dealing with, the food need, the wood needs, it's very difficult to get things going. That is something to work on as well. And then I close with my last slide to show you that there is forest in the Netherlands. And this is a picture of the forest behind my house, where we are going around with our mountain bikes. We dare to call them mountain bikes, even in the Netherlands. So thank you very much.
Thank you, Gert-Jan. And thank you to Marcus, our laureates, all the other speakers, and especially our audience. We have seen how understanding forest growth has progressed from statistical patterns based on past forests to process-based insights that help us understand past and present forests and help us shape the forests of the future. We've learned how understanding processes that control growth lead to landscape-scale predictions of growth by using site-specific information, much of which can be obtained by remote sensing techniques. Forest growth is all about carbon, and forests affect the global carbon cycle, as well as respond to the changes in our climate that are driven by human practices and activities. Our forests are one of the most precious parts of our planet, and virtually all forests are currently affected by people. Some are managed very intensively, with highly selected genotypes being cultivated like agricultural crops, whereas others are in such remote locations that they don't receive direct management. But as we've seen, even unmanaged forests are changing in response to our changing climate. And our influences go even further, as we influence the populations of wildlife species that depend on the forests, and those wildlife species in turn shape our forests. In the 1980s and 1990s, research on the yields of eucalyptus plantations in Brazil focused largely on tree genetics, nutrition management, and silviculture. But since 2000, research has had to increase dramatically with a focus on exotic pests and diseases. We need to keep in mind that forests of our future will be shaped strongly by these sorts of globalization issues of pests and diseases, and that the growth of our forests will not just be a function of the environmental factors of water supply, temperature, nutrient supply, and the things that we could focus on with our models in the 20th century. No forest can remain an island in the 21st century. How will our forest futures shift in response to management, to climate, and to these biotic stresses? How will people and industries that depend on forests adapt to these changes? Well, the best outcomes will depend strongly on the quality and quantity of scientific investigations, particularly the breakthrough achievements that give us powerful new insights, new tools, and new opportunities for sustaining forests, industries, and societies. These are the breakthroughs that the Marcus Wallenberg Prize will continue to celebrate in coming years. Thank you all very much.